We're continuing now with section 8.3, and we're going to be looking at some specific types of sequences, or actually a series, and how we can find their sums. First of all, just a quick reminder, what we've said so far is that to find the sum of a series, we want to take the limit of the sequence of partial sums, where the partial sum, S sub n, is found as the sum as k goes from 0 to n minus 1 of the individual terms a sub k. Or in other words, it's a sub 0 plus a sub 1 plus a sub 2 and so on. Just a comment, S sub n means that we're summing up n terms. And notice that we actually don't go all the way up to n here because we're counting the 0 term as one of our terms. So for example, S2 would be these two terms, the 0th term in the first term, if you will. So we actually only go up to one less than the number n. All right, in general, it's typically somewhat difficult to find the sum of a series just by kind of guessing, since it's often not so easy to find an explicit formula for the sequence of partial sums. We've kind of been lucky in the examples we've looked at so far. In this particular part of the section, we're going to look at two specific special cases where we can find an explicit formula, and that's going to allow us to actually find these sums S sub n. After the end of this section, we'll concentrate for the remainder of the chapter on other types of series where we can't find explicit formulas, and maybe all we can do is decide, for example, does it converge or diverge. But for right now, let's look at the first of our two special cases. The first one is the sum of a geometric series. First of all, if I look at the infinite series, the sum as n goes from 0 to infinity of these geometric terms, a times r to the n. Remember, we looked at the sequence for this too, right? Then, using some algebra, my goal is to find a formula for the nth partial sum, sometimes called the geometric sum of this series. So, I've already kind of filled this out. This isn't something that I expect you to replicate. It's just something that I want you to kind of follow along with, if you will. And here we go. The nth partial sum, as k goes from 0 to n minus 1, of a times r to the k, could be written as a times r to the 0 plus a times r to the first plus a times r to the second, and so on and so on. And my last couple of terms would have an r to the n minus 2, and then finally an r to the n minus 1. In the next line, I'm going to take this series and I'm going to multiply it by r. So the exponent on all the r's is going to go up by 1. So now I'll have a r to the first. This one will become a r to the second. This one will become a r to the third, a r to the fourth, and so on. And now my last two terms, adding 1 to the exponent, a r to the n minus 1, and then finally, just a r to the n. I would now like to subtract these two series. So S sub n minus r times S sub n. And what you'll notice here is there's a whole bunch of terms that are going to cancel out when I do the subtraction. And all I'm going to end up with is the a r to the 0 term minus the a r to the n term. Next up, I'm going to factor out S sub n on that left-hand side. So S sub n times 1 minus r. And on the right-hand side, since r to the 0 power is just 1, that turns into just a minus a r to the n. And if I factor out the a, 1 minus r to the n. All right, I'm going to solve for the sum S sub n. And so all I'm doing here is dividing out this 1 minus r. So I have a times 1 minus r to the n over 1 minus r. And that's going to be equal to what I started with, s sub n, or the sum of ar to the k, as k goes from 0 to 1 minus n. Okay. This is an important formula that we'll be using to find sums. So keep that one in mind, definitely one we'll need. All right, my ultimate goal now is to say, what if I have an infinite number of terms? What if I'm summing up a geometric series with infinitely many terms? So what I want to do, if I'm going to end at infinity up here, is essentially take the limit as n goes to infinity of this formula that I just found. The only place n appears in that formula is right up here in the exponent. And what happens to r to the n power is going to depend on the value of r. If the absolute value of r is less than 1, then r to the n goes to 0. But if the absolute value of r is greater than 1, then r to the n diverges. We saw that back in our sequence work. So what we're going to say is, as long as the absolute value of r is less than 1, and this can be said to go to 0 in the limit, we end up with a times 1 minus 0, or just a on the top, over that 1 minus r. And again, that's only valid when the absolute value of r is less than 1. If the absolute value of r is greater than 1, this diverges. All right, on the next page, that is summarized for us, including the information that we just said. Before I leave this page, there is my second really important formula. We will need that one as well. So I have just rewritten the first formula. This one is for the finite sum. And this is valid for any r, because it's a finite sum, I don't have to worry about it converging. Here's stated as a theorem the final result, the one with the absolute value of r being less than 1, then the infinite sum is a over 1 minus r, but again, only if the absolute value of r is less than 1. Absolute value of r greater than or equal to 1, we get divergence. And there's a little diagram that kind of reminds you of that too. This is the zone that works, right? Just r between negative 1 and 1. All right, so let's go ahead and we're going to use these two formulas as appropriate to find some geometric sums. The first set are going to be finite. Okay, so I'll be using this top formula, the finite sum. In example 1, we say which of them are geometric sums, and if they are, we'll use our formula to evaluate. All right, so looking at this first one, it definitely fits the format for a geometric sum. And if you compare it to our formula, you can see that our a value is 5. The r value, what's being raised to the k power, is 3/4. And then keep in mind, this 10 up on top here is actually n minus 1. So I'm going to have to say n minus 1 is 10. So n would actually be 11. And I'm going to take all of that and plug it into my sum formula for a finite sum. Like so. So we're going to get 5 times 1 minus 3/4 to the 11th power over 1 minus 3/4. Okay. And then it just becomes a calculator problem. Rounding to 3 decimal places, I got 19.155. All right, let's try a couple more. In B, in this case, there's no specific multiplier listed, so you have to imagine that the A value here is just 1, a multiplier of 1 out here. So we'll go with A equals 1. R would be the negative 1/3, what's being raised to the K power. And this 8 is our N minus 1. So N is actually 9 in this case. And so, I won't keep repeating it, but I'm plugging into the same formula, right? A, which is 1, times 1 minus negative 1/3 to the 9th power over 1 minus negative 1/3. And again, that just is a calculator problem. You can plug that right in. And I got 0.75. All right, let's take a look at a couple of other things that can happen. The next problem, part C here. Be careful with this one. This one's not geometric. If you'll notice, in a geometric series, the exponent has to be the variable k. Here the exponent is a constant. K is part of the fraction. So this one I'm just going to say not geometric. Therefore, we could not use our sum formula for geometric series to sum this one up. All right, let's try D. D looks a whole lot better. Again, K here is back in the exponent again, which is what we would expect for a geometric series. And so our A here is 2. The R is the 4. N minus 1 is 6, giving me an N of 7. And it's just a matter now of plugging back into my formula. A, which is 2, times 1 minus R, which is 4, to the 7th power, over 1 minus 4. And again, just a matter of plugging that into a calculator. I got 10,922. Now notice my R value was bigger than 1, but that's okay, because this was a finite sum. I only have to worry about R being less than 1 in the infinite sum, so we haven't done those yet. All right, the last two show you some little variations that can happen. So let's take a look at E next. Sorry, get this so it's not on an angle for you guys. There we go. The issue with this one, there's actually a couple of issues. The first thing that I'm going to notice is the K value here starts at 1 instead of 0. So I'm going to have to deal with that. The second thing that I'm going to notice is that the exponent isn't quite K, it's minus K. Fortunately, I could deal with both of those issues. The way that I'm going to do this is by rewriting a couple of things. First of all, I'm just going to change the K value to 0, and I'll explain how I'll deal with that in just a minute. But I have to have a K of 0 in order to use my formula. So K equals 0 to 15. And then I've got the 3 times. And then instead of 5 to the minus K, I'm going to write that as 1/5 to the K. Notice I used the negative exponent to bring the 5 to the denominator. and then I still have the k power there. This now is something that I could use that formula on. It fits the format exactly. But I have an extra term. I didn't really want to start at 0. I wanted to start at 1. So what I'm going to do is I'm going to subtract the term with k equals 0. 3 times 1/5 to the 0 power. That's just taking out the extra term so that I really only start with k equal 1. All right, a is 3. R is 1/5. And minus 1 is 15, so n is 16. And then I plug everything into my sum formula for the geometric series. And I'm going to get 3 times 1 minus 1/5 to the 16th power over 1 minus 1/5. And then I have to subtract. That would just be 3 times 1, or ultimately just 3. And once again, all this just gets plugged into a calculator. And I actually end up with 0.75 or 3/4 again. So, a couple things to note there. Sometimes things that are almost geometric can be rewritten using a little algebra to make them geometric. And don't be worried about the starting value on k. If you don't want to start at 0, you can always subtract the extra terms to make things work. All right, one more of these finite ones. K equals 0 to 6, so yay, I'm starting at 0, right? But what about this? 2 to the 3k power. I really just want an exponent of k in order to make this fit my format that I need for my sum. So once again, it's going to take a little bit of a rewrite. I'm going to think of that as 2 cubed to the k power, right? When you take a power to a power, you multiply the exponents. So that's the same thing. And so actually, I've got the sum as k goes from 0 to 6 of 8 to the k power. Well, that's good because that now perfectly fits the form that I need. My a value out here is really 1. So a is 1. R is 8. And minus 1 is my 6. So n is 7 here. So I'm going to get 1 times 1 minus 8 to the 7th power over 1 minus 8. And that came out to a large number, 299,593. That's what I got when I plugged that in the calculator. All right, so there are some problems with the finite geometric sums. In example 2, we're going to look at the infinite geometric sums. And just a reminder, with the infinite sums, we now have a new formula, right? Our formula for the infinite sums is a over 1 minus r. So here we go. First one, we've got an a of 5 and an r of 3/4. And that's all I need to know. I just plug into my formula for an infinite sum. 5 over 1 minus 3/4. And that comes out to 20. These are actually less complicated than the finite ones, huh? All right. Take a look at B. B is certainly a geometric sum, but this one I'm concerned about. A is 3, that's no problem. It's the R that I have a problem with. r is 1.5. And since that's greater than 1, I cannot use my formula. That formula is only valid if the absolute value of r is less than 1, right? Since my r is greater than 1, I simply have to say that this diverges. This would go off to infinity. All right, I'll try a couple more. C, I think we're back in business. Our r here is negative 0.3. The absolute value, 0.3, would certainly be less than 1, so we're in good shape. A is 6. R is negative 0.3. Now, I do have an issue here. Notice what the k value starts as, right? K starts at 2 this time. So I can use my geometric sum formula, but I'm going to have to get rid of the k equals 0 and the k equal 1 terms. So I'm thinking of it this way. I know how to find the sum from 0 to infinity. We'll use the formula to do that. But then we're going to subtract the k equals 0. And we're also going to subtract the k equal 1. We're taking out the 2 terms before the one I really want. So this one, I used my formula. Again, a was 6 over 1 minus r, which was negative 0.3. And then I'm subtracting, that's just 6 times 1, or 6. And I'm subtracting this, that's actually a negative times a negative, so that'd be a plus 1.8. Plug it into the calculator, especially for that first term, gave me 0.4154. All right, one more. This one is actually not yet written for us in terms of a sum. We're going to have to do that ourselves. So the first thing I'm going to notice here is, what's my multiplier to go from one term to the next? Times what fraction? 36 times what gives me 30? Well, I can kind of ask myself that question backwards, right? I could take the 30 divided by the 36 and change that to a fraction, and it would be 5/6. And we could check that out. If I take 5/6 times 30, do I get 25? Yes, I do. So indeed, it does look like 5/6 is the common multiplier here. So I can write this then as the sum as k goes from 0 to infinity. My a value or starting value is 36 times 5/6 to the k power. Now that it's written in that geometric format, I can just go ahead and use my formula. Looks like we've got an a of 36 and an r of 5/6. So we'd have 36 over 1 minus 5/6, or 2/16. All right, so there's a few examples for us of using those geometric sum formulas. Keep in mind, always determine first of all, are you using a finite formula or the infinite formula? And then secondly, if you're using the infinite formula, make sure you have an absolute value of r less than 1. Otherwise, you can't use it. All right, we're going to look at a couple of examples of using this formula in some somewhat interesting situations. Turns out that we can actually use this formula to help us change a repeating decimal into a lowest terms fraction. Just all doing the work by hand. So I'm going to start out with the repeating decimal 0.24 repeating. And of course you all know what that means. It's 0.24, 0.24, 24, 24, and so on. And in order to write that as a geometric series, I'm going to rewrite first, kind of separating off each little block or chunk of 0.24. So I'm going to start with the 0.24 here. And then I'm going to add this one, which is actually 0.0024. And then this next one would have 4 zeros in front of it. 24. And then 1, 2, 3, 4, 5, 6 zeros, and then a 24. And so on. Okay. Don't worry about using up the space. I got space at the bottom of the page to do the 0.317. All right. If you think of this as an infinite geometric series, what have we multiplied each term by to get to the next term? Well, to go from here to here, we moved the decimal left 2 places. So that's a multiplier of 0.01. And again here, we've moved our decimal back another 2 places. So multiplier of 0.01. So on. So if I wanted to write this as a geometric series, I could say my A, or my original term, was 0.24, and then I'm multiplying by 0.01 to the k power, however many multiples I need to get to the term I'm looking for, as k goes from 0 to infinity. Well, we've just been working on this formula, right? The A value would be 0.24 over 1 minus the R value of 0.01, which is 0.24 over 0.99. Or if I multiply top and bottom by 100, that would be 24/99. Or in lowest terms, I could divide out a 3, 8/33. So a repeating decimal is really just an infinite geometric series in disguise. Okay. By the way, whoops, if I don't break my calculator first, we can check that one. If you put enough 0.24s in your calculator, eventually your calculator will understand what you want. We go to the math menu and change to a fraction. And there it is. There's that 8/33. All right, this fractal geometry thing is actually on the next page, so I'm going to do part B down here. We have a little bit of extra space. In part B, we have the decimal 0.317 with just the 7 repeating. Now, when only part of my decimal repeats, I kind of have to separate this off and think of it as 2 pieces. The 0.31 is easy to handle. That's 31 hundredths done, right? And then I have 0.007, 7777, etc. I'm going to think of this as 0.31, and then I'm going to start breaking this up just the way I did the last one. I'd have 0.007, and then I'd have 0.0007. That gives me this one. Now this one would have 4 zeros in front of it, and so on. So I've got 0.31 plus, I'm now going to translate the rest of this into an infinite series. My A value is my starting value, 0.007. And then notice, to go from one term of the series to the next, we're always moving our decimal left 1. So that would be a multiplier of 0.1. So my R value here is 0.1 to the K powered. All right, so we got 31/100ths plus, using my geometric series formula here, A is 0.007 divided by 1 minus the 0.1. So I got 31/100ths plus 0.007 over 0.9. And I'd like to make that a regular fraction with no decimals in it, so I need to move the decimal point over 3 places. I'm going to multiply by 1,000, top and bottom. So that's going to give me 7 over 900. Okay. To finish the problem, I would need to add those two fractions, so I would need a common denominator. And let's see, to get that, I just multiply this guy by 9, top and bottom. So 279 over 900 plus 7 over 900 is 286 over 900. And I could divide those by 2, so 143 over 450 would be my lowest terms fraction. Let's see if we can sneak the calculator into doing this one as well. 0.317 with a whole bunch of 7s. Yep, there we go. Oops, sorry, couldn't see that. There it is. 143 over 450. So again, a repeating decimal is really just an infinite geometric series, kind of hiding in there. So there's one application of infinite geometric series. The second one that we're going to take a look at is a fractal. You may have heard of fractals before. Fractals are just geometric shapes that essentially repeat themselves in a smaller and smaller format. So what we've got here is what's called the Cox snowflake. It's a fractal consisting of the union of infinitely many equilateral triangles, as shown in this figure. You start with this large triangle here, and then onto that large triangle, I build a smaller triangle in the middle of each of the 3 sides. On the small triangle, I build smaller triangles. And on those small triangles, I build even smaller ones. And you can see that you could repeat that process indefinitely. Of course, it gets so microscopically small that we can't see it. But essentially, every single triangle that we draw is going to get 2 more little triangles built off the side of it. Okay. Each set of smaller triangles has sides 1/3 the length of the next larger triangle. Our goal is to find the total area of the snowflake, assuming we repeat this process of adding little triangles forever. So here are a couple of assumptions we're going to make. Actually, just one, really. The largest triangle represents the unit of area. So the area of this triangle is 1. And I'm going to start keeping track of these. I'm going to say A0 for my largest triangle has an area of 1. Now, what would the area of the next largest triangle be? Well, we know the sides are all 1/3 as long as the original. And if all the sides are 1/3 as long, the height is also 1/3 as long. So base times height is going to be a third times a third, or a ninth as long. If you don't love that logic, try this. If I were to break this up into smaller triangles, notice for this size triangle, you'd have 1, 2, 3, 4, 5, 6, 7, 8, 9 of them would fit in there. So if you don't like the 1/3 times 1/3 is a ninth logic, you could use the geometry logic that, hey, those smaller triangles are exactly a ninth as big as the original. So I'm going to say A1 is 1/9, and that would refer to all three of these triangles. A2, the next size triangles, which are yellow in my picture, how big are those going to be? Well, let's see. We would have a third as big as this one, both in base and height. And so what we would end up with is a third times the area of this. A third for the base, a third for the height, times the area of the previous size triangle, a ninth, which would give me 1/81st. So all these little yellow ones have area 1/81. We could continue to use this logic. Let me do one more. Let me do the little red ones. A3. Once again, I use a third as big, so a third of the base times a third of the height times the area of the previous one, 1/81st, and that gives me 1/729, etc., etc. In general, to get my area of my nth triangle, notice it's always going to be a third times a third, that's a third of the base, times a third of the height, times the area of the previous triangle, a sub n minus 1. All right, so we've got our areas. Let's think next about how big, or excuse me, about how many of each of these triangles there are. Call that n. Let's see. For n sub 0, there's only one of the original triangles. For n sub 1, there were 3 of these. For n sub 2, we can actually still count at that point. Let's see. The yellow ones, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Make this just a little bigger so I have to keep on moving my paper. And 3. All right, that's the little red one, so I'm going to have to be a little bit more clever here. Let's see here. I'd have, on this white triangle here, I'd have 1, 2, 3, 4, 5, 6, 7, 8. And let's see, I would have to do that. Actually, let me do it this way. Let me count the whole top row. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 on the top row. So 16 here and 16 there would give me a total of 48. All right, I don't particularly want to count anymore. And so what I'm going to notice here is that after the first one, which was sort of an anomaly, it looks like we are multiplying by 4. So I'm going to say that the number of triangles for the nth step would be 4 times the number of triangles for the previous step. All right, I am ready to do my total area now. And I'm a little bit out of space, so I'm going to actually continue on a blank sheet of paper here. Should have given us a little more space on this one, sorry. So here we go. I'm going to start by saying that first one was kind of an anomaly, so I'm going to do that separately. I'm going to say for an n of 0, the number of triangles was 1, and the area of that triangle was also 1. And so I have one triangle with area 1 for a total of 1. After that, I should be able to start establishing a pattern. When n is little 1, or excuse me, when n is 1, little n is 1 is what I meant to say. N1 is 3. There were 3 triangles. A1 was 1/9. So 3 triangles with an area of 1/9 each would give me 1/3. All right. When n is 2. See, when n is 2, there were 12 triangles. Each triangle had an area of 1/81. So my total area there would be 12 times 1/81, giving me 12/81. All right. When n is 3, we had 48 triangles. Each one had an area of 1/729. And let's see, if I take 48 times 1/729, that gives me the total area for those of 48/729. All right, of course, we would want to complete that pattern, but I think we're hoping at least we're going to be able to kind of see what's going on here. Let's see here. First of all, I'd like to see what's going on as far as a constant multiplier. I know this first one is a special case, right? It was before the pattern was established. We saw that it didn't really fit the times 4 pattern here. So I'm not going to worry too much about that first one. I'm just going to treat that separately. But for these, we saw a definite pattern. Right? These were all multiplied by 4, right? Times 4, times 4. And these were multiplied by 1/9. Therefore, these better be multiplied by 4/9. And you can check that. If you were to take 1/3 and multiply by 4/9, you would get that lovely decimal. Check and see if that's the same thing as 12/81. And indeed it is. Take that 12/81 times 4/9, and I get that. Check and see if that's the same as 48/729. And in fact, it is. So, if I wanted to turn this total area into a sum, I'm going to start here before the pattern is established with my 1. And then I'm going to add the sum of all of these. Okay. The first one is 1/3. And I'm going to multiply that by 4/9 to the k power. And we're going to go from k, k goes from 0 to infinity. We're going to go on forever. So we're going to get 1 plus. And here we go. Here's my infinite sum pattern. A is 1/3 over 1 minus r, which is 4/9. And when I do that on a calculator, I get 1.6 for the total area of that snowflake. So areas of fractals, another kind of interesting little application of our infinite series. All right, that brings us to the end of section 8.3.